to start off with, you all know the basic theory that as the globe warms up, there's more energy. More energy means more severe weather, more evaporation, more rainfall, but at the same time more intense sunshine, giving droughts, floods, more extreme weather. And what have we seen? Well, the thing that's been weather-wise, that's been most in the news recently, is the drought in the US that you might have heard about. And lo and behold, there's a pissed off US farmer, and what's happened there? And there we go, that's the US drought. There's a map to prove it's happening. But of course, related to that, that's fires in Colorado. But of course, you might have heard of quite a few other funny, weird weather that would have been happening. And as you know, one way that we're all aware, even people that don't know anything about climate change or the theory, they get this feeling that the weather's going a bit weird from the news reports from around the world. So that's forest fires in Colorado, that's forest fires in Spain. I think there have been forest fires in Spain this year, but also in previous years, and Portugal. That's actually 2009 from Victoria State in Australia when there were horrendous bushfires, you might remember. That's Greece, the fires in 2007 were particularly severe, do you remember that on the news? That's Greece in 2009 above the Parliament building, the smog again. That's Greece this year, so it's still happening in the Mediterranean regions. Then there are floods. That's Peking a couple of months ago, floods in Peking, do you remember that? That's Thailand over Christmas. There were big floods there, they were also on the news. Then there were floods in Pakistan. That's actually last year, but you may be thinking, wasn't that actually 2 years ago? Well, of course it was 2 years ago as well, when the floods were even bigger in Pakistan. And then at the same time, that year, 2010, that's a sort of smog over, you might recognise the Basils, in Red Square, and there were fires in Russia, forest fires all over the place because of a massive heat wave in Russia with extraordinary temperatures breaking all the records in 2010. That's Niger, droughts in Niger that we've been getting actually year after year, and I'm not quite sure which ones were the most intense. But hot on the heels of the droughts come floods also in Niger, and there's a sort of irony in that, but the destructive impact of both on food supplies, malnutrition, and malnutrition-related diseases. But the other thing we're also seeing, now that's an ice storm in the US, and you can see, and I think that was 2010, I'm not sure, and that's the kind of thing with loads of snow being dumped across. And then you're looking at things that's a little bit harder, isn't it, to explain to people, what's this cold weather got to do with climate change? But we're seeing all sorts of weather extremes. This is the May and June, or whichever months it was, which broke all the records for rainfall this year in the UK, and you can see that represented on the map with record rainfall. There we go. That's everything blue. The dark blue is 200 times the average, or 200% of the average. Sorry, 200% of the average. Yet at the same time, you may remember at the beginning of the year they were talking about a hosepipe ban because of very dry winters, because we're not getting the rain in the winter, which is what really counts. And with that, there have actually been some exceptionally cold winters, and hasn't that been difficult to explain to people climate change-wise? In the Daily Mail saying global warming, don't be ridiculous. And even penguins cited in the UK, as you can see. And that is the winter of 2009. But even more severe or exceptional was December 2010, when it was incredibly cold for December. You thought January maybe, but December. Now, of course, what you have to do is look at the temperature anomaly map. So that's not the temperature, but that's the change from normal. But that is for December 2010. And this is what you need to show people, isn't it? To show them that dark blue area around Western Europe, that was when it was exceptionally cold. But at the same time, as George Monbiot pointed out, it's exceptionally warm in Western Greenland. So of course, that's the first principle. Is it localized? It's localized change when it's cold weather. It's not the whole planet, and obviously it's the average across the planet that matters. And so you can get exceptionally localized cold weather, but it can be exceptionally warm somewhere else that balances it. And now, but it's still quite difficult to explain, you know, directly what, you know, how does this cold weather and stuff relate, you know, what has this got to do with climate change? Isn't it just sort of random change or something? Now, recent studies have elucidated this. I mean, I've only really spotted it this year. Some clever people might have spotted it earlier. But a lot of these weather incidents have to do with the jet stream, we're told. And in particular, for instance, the Russian drought, there was a blocking mechanism where the jet stream got stuck in one place, and because it didn't move, instead of having like a few days of hot weather, you had like months, so the temperature goes up and up and up, and you get a heat wave because the jet stream gets stuck in one position. That's partly because the jet stream has got weaker, more sluggish, so it gets stuck more often, but also at the same time as getting weaker, what's happened to it is it's a bit like when a river comes off, you know, it's a torrent up in the hills and it goes zoom straight down, and when it gets down to the plain it wanders around, it meanders more. So the jet stream, as it gets weaker, it meanders more. So what happens then is something like this, so that it means the meandering means there's more north-south, so it's west-east direction, this is the northern jet stream, and it meanders more, it means there's more north-south movement, so you get cold air moving further south than normal, and you get warm air moving further north. So this is what happened with that cold December. The cold air came right down here, and not only that, but it stuck there for quite a long time. So this is all related to the jet stream, and then the warm air gave a cold Greenland, and then that's another way of looking at the same thing, with a big high over Greenland there. And this, now, going back to the Russian drought, this is what happened for the Russian drought. This is the jet stream, this white thing, and it looped up far north and stuck there, which allowed all this hot African air to come over Russia and give that heat wave. But at the same time, cold, moist air came down to Pakistan, met the monsoon winds, and you got floods in Pakistan at the same time. So they were both related to this jet stream extra meandering blocking event, if I can put it that way. And then that's a similar, that is, at any rate, that sort of shows the kind of thing that is happening in the US that explains the current drought. So there's this warm air stuck in this loop of the jet stream over a lot of the US. And this is like the cold patch in the UK with the warm air up over Greenland. This is the jet stream being forced further south, and all the cyclonic weather being forced over Britain and sticking there for a long time, giving us all that wet weather. Now, what is this? This is all happening because it's being masterminded by this polar bear in the Arctic. So and the point is that all this weather is actually related to what's happening in the Arctic, so it seems, because the jet stream actually gets its power. It's on the boundary between the cold mass of air of the Arctic, as you saw there, and the temperate air. And the temperature gradient between the two, which is related directly to pressure, is what gives the jet stream its power. So what's actually happening is that this is a temperature anomaly map again, so it's a difference from normal, not temperature, but difference from normal temperature. And what's happening is the Arctic is warming up much quicker than anywhere else. I mean, I've read 3 to 4 times quicker from some people. So the result is that the difference between the Arctic and the temperature is getting less. So as the temperature gradient gets less, there's less power in the jet stream. So that's why, if you can just, because otherwise we know.
On that point, just the geological record has it that the poles, I think I'm right in saying, it's 6 times the speed of warm and cold of the global.
Yeah, okay.
Just on that point.
Yeah, okay,
on
fine.
the geological record.
Yeah, yeah. So the point in principle. Anyway. So that's why it's affecting. So this is quite important, because you think, what has all this weird weather got to do with climate change? Well, this establishes exactly what's going on, and it's all very much a part of climate change. And not only that, but it's related to the most obvious visible impact of climate change, which is on the Arctic, which has become, as I'm sure you're all aware, exceptionally visible this year because we've broken the record. Previously, that's the difference between 2007 and 1979 for Arctic cover at its lowest point in late summer. And this year, we've broken that record, and it's even less. That's actually the 23rd of August, diminished, and of course it's got smaller since then. But on the 24th of August, the day after that, it broke the record for ice extent. And not only that, it did it a month before it reaches its lowest point, which is ridiculous, you know. So it's way off. And if you look at this, where it is now is about that distance. Well, it's about 3.5, so it's somewhere down here. So it's dropped off that graph. It's way down here. So it's just a collapse in Arctic ice that's happening. And so...
You're saying that's hard there, is that right?
No, this is 4.0. I'm saying it's down here. It's about 3.5.
Since 78, that's 80. Yeah, okay.
Yeah. And now if you look at the, Brian will say some more about this, but if you look at the thickness of the ice, it's even worse. That's actually between 2007 and 1989. But the thick ice is disappearing. And if you look at the volume of ice, this is the biomass figures from the Polar Institute for something or other. And that's even more frightening. This is the volume of Arctic ice. Now, if you put an exponential curve through that, that takes you to 0 in 2015. And Peter Wadhams, who doesn't represent the scientific consensus, he represents the scientists with the most radical projections on this, because he's been studying the volume of ice from submarines for the last 40 years. He's predicted since 2008 that it's going to hit 0 by it's all going to disappear, essentially, by late summer 2015. I mean, so that's what we're looking at. But you can see how the volume is going. And another one, related to that is increased melt on Greenland. Melting, it's never melted that much since the 19th century, or been melting all over. It doesn't normally do that. But this is related to the weather. Like I said, that's the important point. It's all happening now, and these are how is this actually affecting us now. And how is it destroying lives and livelihoods now? Well, this is the Russian drought as related to grain-producing regions, and there's quite an overlap, as you can see. And of course, Putin put an embargo on grain in 2010, which is all dead, as you can see from that picture, which proves it definitively. Then there's riots, food riots in Mozambique in 2010, as there were in other places. We've now got that's the corn in the US, and as you can see, that's dead, and food prices are, hitting the roof now, and we're just waiting to see the impacts of that around the world in terms of food prices, food shortages, civil unrest, and so on. And so that's all happening. That's all happening now, and it's all related to the Arctic, but it doesn't stay in the Arctic. There are other things related to the Arctic that are also scary, and of course, I'm sure you've heard about this. This is the permafrost, and that will certainly be, is already releasing methane, which will accelerate global warming. It's just a question of how fast it releases, but potentially, that's how much carbon content there is in the permafrost compared to the atmosphere, so it could double it several times over. It's all there. And even more scary, you would have heard about methane hydrates, and this part of, and that's a crystalline structure. It's all the sort of dead organic matter that's come down in rivers and plankton and stuff, accumulated at the bottom of the ocean in a crystalline structure. It's kept in that form by a mixture of pressure and temperature, but if you alter sufficiently those two factors, it bubbles up. And it's most closest to the surface in the East Siberian Arctic shelf, where there's most of it. But this is the big, scary thing, because that's, when you're looking at total recoverable, non-recoverable fossil fuels, which would cook the planet several times over, and then you look at the gas hydrates, that's very approximate, that, but it's something like that. Then it's out of it, then it's, obviously you're not expecting those all to appear at the same time, but potentially, I mean, that's doom. And the point about the point that's often made about the methane hydrates is that they are linked. They are thought as the most likely cause of extinction events, like the big Permian extinction event and the end of the Eocene, I forget the correct name, extinction events, and they've been associated with what Hansen calls the methane gun. So in other words, you know, it's waiting to go off if it's loaded as it is now, i.e. there's a lot of methane hydrates around the planet. So that's all happening now. That's the point that I want to make. And what you've got to bear in mind that what's happening with these weather disasters and feed-through effects hitting human populations already is that it's not going to get any better. It's absolutely not going to get any better. There's no going back. You know, when we deflect from the normal, that it's intuitive to think we'll go back to the normal at some stage. We won't. This is the beginning of a slope we started down and we're not going back up. It's just going to get worse. We don't know how fast it's going to get worse. If I can rush on and we'll have questions at the end. I'm going back to a little bit of basics now in terms to put this in the perspective of what we know about climate change. So I'm sure you're all familiar with that kind of picture. And that's the temperature rise. We all know about that. We also know that when we're talking about it, we insist to people, temperature rise doesn't seem much. It's when you look at the rise in carbon dioxide in the atmosphere that you get that thing that is as scary as it looks. And the critical graph is this one. So you can tell to people, look, there's global temperature, there's CO2. The two are closely linked for the last 450,000 years over the interglacial and then Ice Age, interglacial Ice Age. The two are closely linked, aren't they? How can you possibly deny that? They are closely linked until you get to now, when whoosh, the CO2 levels go up there, leaving the temperature still where you've seen it for, the same as the previous peaks. But common sense suggests that the temperature is going to follow the carbon up there. And of course, common sense isn't enough, but the science more or less supports that. That's the problem. So, that is the best. If you're trying to explain climate change to people, that slide or version of it, that picture is the best one to show because it really sort of summarises most what's going on. And when, everything we looked at before is a part of this starting to chase that up there. Now, to understand this better, what you do need to say, somebody might say to you, but it wasn't carbon dioxide that actually triggered the ice ages. So, when you saw the ice ages in that graph before, what actually triggered the ice age to interglacial and back again is actually little changes in the orbit and the axis of the Earth. And in fact, if you're very clever, you can put all those three together, work out the solar forcing and see that it relates to the stages of glaciation. But the really important thing to realise is that this is only the trigger. It's a tiny forcing. It's a tiny sort of push to the system. It only had any effect because this is from James Hansen's PowerPoint, so I've pillaged everybody. It's the chief instigator is the orbital change, but a very weak forcing. The chief mechanism is actually CO2, greenhouse gases. And the other thing is a change in the Earth's reflectivity through the melting of the ice caps. Now that should make you feel send a little shiver down your spine, because we've just seen, at least for a proportion of the year, the planet's ice sheets disappearing or getting smaller. So we've actually got both of these feedback mechanisms now in operation. CO2, but also the ice sheet area. That's happening now, we're doing that. And these are what really caused the change in temperature in the ice age. They were the motor for it. The little orbital changes were just the trigger. And so Hansen goes on to make some other points. So climate on long time scales is very sensitive to very small forcings. So this happens over eons of time, but a little push, and then thousands of years, it has a big impact. That's how the ice age has happened. But by comparison, human forcings are much bigger, and we'll return to that anyway. But for the moment, we're just going to, this is David Wasdell's projection. Now let's just see how much time I've got left. So I'm probably going to have to actually rush through this or I'll never get there. That is concentration of CO2 in the atmosphere, and that's temperature, plotted one against another. I'll just rush through that one. Now, he puts it to a logarithmic scale. That means that's the same graph, but you've straightened out the line by putting it on a logarithmic scale. Now, this is what CO2, that 280, that's the benchmark, pre-industrial benchmark, when it was 280 parts per million. Now, the effect of CO2 on its own, you know, retaining heat that otherwise would be reflected away, has this effect. If you double the CO2, it increases the temperature by 1.2. And so for 440 PM, it gives you like just under 1 degree centigrade. So that actually isn't that much, but we've known since, I'll rush on, we've known since the 70s, this is late 70s science, Charney, that if you, the reality is that what controls how much happens is the feedback. So the CO2 is augmented by feedbacks. That's the important point. So modelling and stuff back in the 70s gave you this, and this is what the whole IPCC projections is based on. It's saying that if we go to 440 PM, we will get a rise of 2 degrees centigrade. So they're saying if we can keep parts per million to 440, we won't go more than 2 degrees. The whole thing is based on that. However, when you look at the Hadley Centre, they've included more of the feedbacks, and that gives you that. Let's go on. If you go to Hansen, it's like that, and you'll be familiar with the figure 350. So it's the figure 350 here that gives you 2 degrees, according to Hansen. And this is Wasdell's Earth system sensitivity. Now he bases this on paleo evidence purely. He says that actually, by coincidence, if you take 440 PM, if you take the 280 to 440, whatever that makes, and you take the same amount and deduct it, you happen to end up at a figure of 180, which is what it was at the depth of the Ice Age. So the depth of the Ice Age was 180 ppm, and the temperature was 5 degrees less than now. So back of the envelope, common sense, work it out in your head, you'd expect that if you add that, you'd be 5 degrees warmer. That's what that line is saying. It's pretty simple. Now, he backs that up with 2 other points. That's plotting the average ppm to temperature during the ice ages, and that's the average of the Pliocene before there was a northern ice sheet. So, you know, it looks like that's it. Now, at this point, you have to make a really important distinction to really understand what's going on. There are fast feedbacks that happen quickly, like, say, water vapour. As soon as the temperature goes up, you get more water vapour. That's another greenhouse gas. That's an instant feedback. Some feedbacks are slow and take a long time. So, for instance, if you remove the ice caps, there's less heat reflected away. That's a feedback. You know, it's making the situation worse. But, of course, it takes hundreds of years. It's a lot of ice up there. It's not going to go like that. So that's a slow feedback. So what I'm saying here is basically we're totally in the deep brown stuff, because 440 PM, that we're heading well over that, gives us 5 degrees, not 2 degrees. But it all depends on how fast the feedbacks really are, how fast are the slow feedbacks. So we have a window of opportunity. Basically what this guy, what Hansen is saying, is we not only need to stop putting CO2 into the atmosphere, we need to take it out again. But the real situation is, how fast is this going to hit us? And I could say a bit more about that, but I don't think I've got the time. This is looking at, this is the temperature change over the last 60 million years, and you can see it was a lot warmer before. When the Antarctic formed, it reflected heat away and the temperature plunged, you can see. And the reason that the driving there was not actually the orbit and all that, it was pure CO2. And the CO2 was absorbed, that's why the temperature came down, that's why we're cooler than it was then, because of this mountain building episode. Mountain building episodes caused by continental drift are what absorbs the erosion of the mountains, draws down CO2 over a very, very long time period. So that's it. But window of opportunity, the problem is redefined by, it's all about how fast things are happening. How fast we can reduce emissions into the atmosphere to 0 and reduce the total amount of CO2 in the atmosphere to, I would say, 320 ppm. Hansen would say, well, he would probably say that as well, but they've used the figure 350 because it's a sort of round figure. And it doesn't make them look like they're saying something too extreme, relatively speaking. So in this context, the feedbacks are really critical. But the other thing to bear in mind, I think you really need for an understanding of what's going on, is that those big changes over, from the paleo record, from geological history, the parts per million of CO2 in the atmosphere were changing at 0.001 part per million per year. We're changing them at 2 parts per million per year. So we'll actually impact the system much faster than has happened before. So that really takes us in. The other thing he's saying is the Antarctic ice started to form when CO2, you remember that, the thing from 60 million years, when it dipped below 450 parts per million, then the Antarctic started to form. So obviously when it goes above 450, the Antarctic starts to disappear. But look, focus on this figure. Here's another way of putting it. Historically, a change in CO2 concentration of 100 ppm has taken place over a period of some 10,000 years. Humanity is generating the same change in 30 years. And then he's put it also in a different way, which I won't go into. So the thing is that what I told you about fast and slow feedbacks is one thing, but also what you've got to add into that mix is we don't really know, uncharted territory, the impact of just changing the system so fast, because that changes the whole feedback tipping point situation. So that means that we're already totally over the limit in terms of long-term climate stability. So the idea that we have a budget of carbon dioxide we can share out, which all the international climate talks are based on, is just not true, not for the long term. We have an emergency that we have to deal with. That's the real situation. And but also we don't know what's going to happen in terms of how fast things are going to go wrong, because we're just impacting the system much quicker than has happened before. So it's kind of like we know it's going to be bad, we just don't know quite how bad or how fast it's going to get. So abrupt change in tipping points. It's about tipping points. And I'll rush on, rush through this because we haven't got time.